Hello, students. Happy Monday. Happy Monday. I am making this recording on a Monday, and sorry about the late recording, but here's the only time that I had to do this. Welcome to week 3 of this course. And congratulations on making it so far. Today we're going to really quickly talk about the items that we're going to be covering in week 3. And it's really about Boolean logic, truth tables, simplification of Boolean expressions, logic gates. We're going to be learning about this AND, OR, XOR, NAND operations, and some implementation of Boolean expressions in them. And we're going to touch on sequential circuits real briefly, but this would be something that I would encourage you folks to read on if we can get through to all of this. There's a lot of work, a lot of readings in the coming weeks. Okay, so that's the scope of week 3. All right, so Boolean algebra. I am going to skip through some of these slides that just give you historical context, but basically, you all know Booleans are just Boolean values, binary 2, a base 2. And these are values that can either be 0 or 1. And you have Boolean logic. Boolean logic powers digital computer circuits. And we're going to be learning about Boolean algebra. There's some historical context here that you can read about just Boolean algebra. We don't have to go in this because of time pressure. We're going to skip all the historical context. I talked about the fact that Booleans are just values that can be either true or false, 0 or 1, on or off, like a switch. A light switch, those are Booleans. We talked about that in previous lessons. So we're going to start learning about what we call Boolean operators. You have two values. In base 10 arithmetic, you can add, you can subtract, you can divide. No such thing as in Boolean algebra, not as much. You have stuff like AND operators. We're going to be talking about that. OR operators, not operators, XOR operators. These are the operators that you can apply when you have two components, two parts in a function that are Boolean representations. Okay, so you learn about the whole concept of a truth table. This is a truth table. This looks like this is a truth table. A truth table is you take two inputs, and the result of the two inputs with some operator equals to an output. Okay. In this case, this is the truth table of an AND operator, and this one is the truth table of an OR operator. And this is saying that when you do X and Y, where X is 0 and Y is 0, the result is 0. If you do X and Y, where X is 0 and Y is 1, the result is a 1. Now, this XY is the representation of X and Y. In some other textbooks, you will see it as represented as X dot Y. X dot Y, okay, but in this case it's just X, Y, and then for the OR, is typically represented as X plus Y, okay. So the sign that you see for AND operators is a dot, and the sign you see for OR operators is a plus. Just one moment, let me grab my textbook. I'll be right back. Okay, so my textbook is just on the floor. All right, so let's keep moving. We'll keep going on. Excuse me. All right, so let's keep moving. So that's that's a truth table for an AND and OR operator. Pretty straightforward stuff. And one of the ways I used to learn this is that for an AND operation, you get a 1 only if all the inputs are 1. All the inputs are 1. So X is 1, Y is 1. That's only when you'd get the result equal to 1 for an AND operator. It's reversed for an OR operator. You get a 0 only if all the inputs leading into that OR operation is 0, right? So that's what you see here, that for an AND, if all the inputs are 1, you get a 1 for the output. And for an OR, if all the inputs are 0, you get a 0 for the output. Okay, so that's one of the ways that I kind of remind myself between the AND and the OR operators. All right, so let's keep moving. So that's the truth table for AND and OR operators. Let's go. Now, this is a truth table for a NOT operator. Think of a NOT as a complement, is like a complement, one complement, right? So typically for the not operator, there's one single input. If the input is x, the complement of x is 1. If the input is 0, if x is 0, the complement is 1. If x is 1, its complement is 0. And that's what you call the not operators, really like a complement. And it's represented using this this exclamation thing here, or in some cases over bar. Okay, so that is a not operator. Okay, so this is a Boolean function. You know, just like any regular function, it has at least one Boolean variable, at least one Boolean operator. We talked about the operator as the OR operator, the AND operator, the NOT operator, and at least one input from the set of 0 to 1, 0 and 1, because again, Booleans are values that go between 0 and 1. Okay, so if this is an example of a Boolean function. If this is a Boolean function that takes inputs x, y, and z, the function equal to x. Can anybody guess what this is? Is this an AND, or what's the relationship between x and z here? This would be an OR. So x ORed with z complement. All of this together ended with a y. Okay? So I'm going to do something here real quick. I'm going to open a notepad that I have here. So this does the same operation there. It's x ANDed with z complement plus y. And now there's precedence in the operations. If we explicitly call it out, the operations is x AND with z complement ORed with y. And there's precedence, right? So AND usually comes first. So if you want to apply bracket, you'd apply a bracket outside of the x and the z prime or complement, or with y. Why? Because the order of operations goes like this. The complement takes precedence, the AND is the next that takes precedence, and then the OR is the last in this particular example. Okay, so hopefully that didn't confuse you all too much, but there's just order of operations where the complement comes first, the AND is next, and then the OR operations. All right. This is what I think. Let's see. Yes, so Boolean operators have rules of precedence, which is what I talked about. The NOT operator, that's the complement, has the highest priority, followed by the AND and the OR. And that's why you saw that I mentioned that in this case, the way this thing is going to be executed by the operating system or by the computer is that this is going to be executed first, then this block is going to be executed next, and then this entire block is going to be executed last. If you look at this example here, right, this example here, which I took from the textbook, x and y ORed with x complement and z ORed with y and z, spelled out like this. The way it's going to be executed by the operating system is that this is going to be executed first, this is going to be executed next, but before this is executed, this is going to be executed first, and then this is going to be executed, and then these two can be executed, and then the result of this executed with this. With an OR operator, it doesn't really matter. There's one of the rules of Boolean, which I think is the associative rule. I cannot remember, but if we move these things around, if I was to take this, for example, and put it here, the result, and I'll do like OR like this, the result really should not matter. Okay, so that's that one. So that's a NOT operator. That's Boolean. This is the truth table for complex function, and what we're just illustrating here is that to find the output of this 3 using this function above, right? We're gonna first of all compute the value of z complement, sorry about that, which is 1 if z is 0. Then we're going to compute the result of x and z complement. Remember, if z complement is 1 and x is 0, that's going to be a 0, right? For an AND operation, the only time you get a 1 is when all the inputs are 1. And this x and with z complement ORed with a y, where y is 0, is going to be 0. Why? Because this x ended with z complement is a 0, ORed with a 0 is a 0. Remember, in the OR operations, if all inputs are 0, the result is a 0. Okay, so that's what this truth table is all about. So a very important concept to get the result of Boolean algebra. Okay, digital computers contain circuits that implement Boolean functions. When you look at a transistor, when you look at a motherboard with all those transistors, the most common basic function or component in that circuit board is Boolean logic gates. We're going to be looking at next, and logic gates just implement these Boolean functions. Okay, so let's skip this. You guys can read through this. If you have any questions, let me know. This one talks about Boolean identities. So there's a concept in Boolean algebra called Boolean identities, and this is covered in page 138 of your textbook. Okay, identities just represent certain laws around Boolean algebra. So if you look at this one, the identity law, this first one, the identity law says that if you perform an AND operation between a value, a Boolean value, and a 1, the result of that is the value. If the value is x, and you perform an AND operation between that value x and a 1, the result is 1. Think about this as 1 multiplied by x equal to x. Same thing here. If you perform an OR operation between a value and 0, you get the value. That is what they call the identity law in Boolean algebra. There's something called the null law, right? Again, if you do an AND operation between a 0 and a value, you get 0. If you do an OR operation between a 1 and a value, you get the 1. Okay, so that's a different law. Idempotent law, again, if you do AND between the value and itself, it's just the value. Okay, 1 ANDed with 1 is equal to 1. All right, so that's the idempotent law. And you hear this in computer science. For those of you who've written code, you typically have the idempotency in functions, which means that when a function executes numerous times, it should not happen. The impact on the output should not change. So for example, if you have a function that executes against somebody's bank account, and that function executes multiple times, the balance should not be reducing if the input parameters of that function has not changed. Okay, that's idempotency. Okay, so read about these laws. There's a lot of them. The key ones that you want to pay attention to. Idempotency is important. The distributive law is a very important one to pay attention to, right? So this is one of those laws where if you have an AND, input is x plus y, z, and you expand this is equivalent to ORing x and y, ANDing that with x or z. It's an interesting one. Okay, so pay attention to this ones. Nothing for me to explain here, very straightforward stuff. If you have any questions, let me know. De Morgan's law is another important one. What it says is that if you take x ANDed with y, that is equivalent to x prime or x complement ORed with y complement. Let's take an example. Let's say x is equal to, let's do this one, De Morgan's law. So De Morgan says, we'll be real quick here. De Morgan says this. De Morgan says that, let's see if I can remember that. It says x and y is equal to x prime ORed with y prime. Let's use an example. Let's say x is equal to 1 ORed with 0. De Morgan says is equivalent to the complement of x is 0 ORed with the complement of y. If y was 0, its complement of 1. Now let's see what happens here. We know that 1 ORed, the value of 1 ANDed with 0 equal to 0. And we also know that the value of 0 ORed with 1 is 1. So what is De Morgan saying here? Let me see. and form x. I wonder if this is a typo. Morgan's law. Oh yes, this is a typo in the slides, folks. I should have given you folks this as an exercise. Somebody tell me what is wrong with this one and get back to me, okay? All right, keep moving. So De Morgan's law, a slide deck may have an issue. Verify that in your textbook. But De Morgan's law is a very important law to be aware of. Okay, so let's keep moving. Where are we here? We are on, let's see. Yes, De Morgan's. So here's a bunch of laws that you want to take a look at again. Page 139 of the textbook covers all these laws. Identity, we talked about that. Inverse law. This is the inverse law. Read about all these laws, and if you have any questions, please let me know. And again, there's always a lot of great YouTube videos that you can leverage to learn some of these concepts. All right. Okay, let's see. De Morgan's, we can skip this one. We talked about that. And so one of the things that you'd appreciate about these Boolean laws is that they help us to simplify complex functions, right? So if you look at this function like this, we can use those laws to simplify this function, this particular function, right? So if you look at this first one, I think they use the De Morgan's law for this first application, and then they use some other law to get from here to here, and some other law to get from here to here. And if you keep following that, you would simplify the function to something very, very simple. That's how these Boolean identities come into play. I'll let you folks work through some examples, but I'll skip through these ones. But again, just remember Boolean identities are some rules that we can leverage to simplify complex Boolean functions. All right, so let's skip this one through table. It just talks about using an example. This again is another example. There's some key terms about sum of products. The sum of products form sum of product. A product is if you have X and Y and the sum of those products. So this is what they're talking about here. But you use one of those Boolean identity laws to kind of simplify this original function to get something simpler. That's really what the goal of those Boolean identities are. Okay? So I sped through sections 3.1 to 3.2, Boolean operators and, ors, nots, truth tables. We talked about that. We talked about Boolean identities. I think those are the three main key concepts within those sections that you want to pay attention to. And again, those Boolean identities, take a look at the De Morgan's an interesting one. Take a look at a distributive law. It's an interesting one. Identities law. Just understand them and how to apply them to simplify the Boolean equation. Okay, so let's talk about logic gates. Logic gates are those components in a digital circuitry that take two inputs and provide an output. So logic gates do the same thing as a Boolean operator. They take two inputs and they represent an output. But we use some hardware to build them. So in this section, we're going to be learning about some logic gates. So a gate is an electronic device that produces a result based on two or more inputs. Okay, so in reality, gates consist of 1 to 6 transistors, but digital designers think of them as a single unit, right? So a gate consists of all these transistors, and a transistor takes a signal and inverts the signal to a different format. So a logic gate is really an electronic device. Okay, so here's some examples. This first one, if you all remember the truth table for an AND, which we looked at in prior slides before, this is the truth table of an AND operation. And that truth table of an AND operation is represented by this logic gate right here, the first one. Okay, the first one. Now, this truth table of the OR operator is represented by the second logic gate. You can see the input of X and Y for the AND logic gate results to X and Y. The input of X and Y in the second logic gate results to X or Y, and the input of X in this NOT logic gate is a complement of X, right? So you all remember these truth tables. These are the electronic devices that are actually used to perform these kinds of operations in a computing device. Okay, so you can imagine there's a lot of these that create your computer. So let's keep moving forward and see what we can do with these things. There's some other ones. Another useful one is the XOR. XOR. Think of an XOR. It's an interesting one. So X XORed with Y gives you these results. And XOR is represented as a plus with a circle over it. Right? So if you think about it, if this is an OR, the XOR is the same as an OR sign with this additional curved lens at the end. Okay, and note that the special symbol for the XOR operation. And with this one, the input is a 1 if either of the inputs is a 1. If both inputs are the same, you get a 0. Okay, so that's one of the ways that I can remember the XOR operation. So I hope this makes sense. Interesting stuff. Let's keep moving. Let's see what we have here. Some other interesting ones are the NAND and the NOR. These are two very important gates. And with the NAND, think about the NAND as the reverse of an AND. Okay, and NAND is almost like a complement AND. So if you think about it, if this was an AND gate, which a couple of slides prior, I showed you all an AND gate, which is this one. Notice that the AND gate does not have that little bubble at the edge, at the bottom of the output pin. Whereas the NAND has one. You see that? So that's a key distinguishing signal right there, sign right there. Then if you see that circle just at the very tip of the output, you know that's a NAND, and that's typically a complement of an AND. You know, so if for the AND operation, remember, we have a 1 only if both the inputs are 1. With a NAND, it's reversed, where you have a 0 only if both inputs are 1. And it's the same thing with a NOR. A NOR is just the reverse. This one, a NOR is the reverse of an OR. So you take the OR operation and you complement that. And again, the main distinguishing factor is that you have this bubble at the top. But there's something interesting here. For the AND or the NOR, the NAND is equivalent to this one, where you're complementing the inputs. You do an OR operation on that complement, and that becomes equal to the NAND. This must be covered by one of those laws that we talked about. Okay, and the same thing with this one. So study that, pay attention to the details, and if you have any questions, let me know. So here we're talking about we're going further on this logic gates. Remember, this is an AND. No, this is a NAND. Remember, X, Y, you have that bubble here to represent the complement. And this is one of those, this is a universal gate because we're taking the input and applying the input to itself to give you this output. Right, so this is XY complement. And then we apply another complement on top of that. A reverse complement gives you the original value. And they call these universal gates because they're inexpensive to manufacture. Okay? So NAND and NOR, this is a representation, Boolean function, this is a representation of a NAND, and a NOR, this is a NOT. So study this and get some clarity on it. If you have any questions, let me know. I think we can skip this. We talked about logic gates. These ones have 3 inputs, but the same rules apply. For an OR gate, it's X or Y ORed with Z. For an AND gate, it's the same thing. So just study that. If you have any questions, let me know. But it's the same kind of thing. Okay, so those are logic gates. Now, there's a concept in Boolean algebra called Karnaugh maps. Karnaugh maps. Karnaugh maps are covered in section 3.4. Karnaugh maps they're a graphical way to represent Boolean functions. Think about this as a graphical way to represent Boolean functions. And our slide that says is a simplification of Boolean functions. It says, let's see if we have a definition here. This is the historical context of the Karnaugh map. But here it talks about it's a graphical representation to illustrate digital functions. Okay, so you can read through this, but there's some key terminology called min terms that apply to a Karnaugh map. And the definition of a min term is also given in your textbook on that same page, page 149. But if you have inputs into a function such as x and y, the min terms will be the combination, the ANDed combination of all these inputs and their complements. So for example, if you have x and y, min term is going to be x complement and with y complement, and so on and so forth. Okay? So consider a Boolean function function of x and y is equal to x and y. Its min terms are going to be x complement with y complement, x complement with y, x, y complement, x and y. Those are min terms. You take the inputs and you do an AND operation in them with these values and their complements. We can do something similar for a larger function like this one. We're not going to go through that. If you have 3 parameters, you're going to have 8 possible outputs. So let's not go through that. But, so here's what the Karnaugh map starts to look like. If you take a simple truth table like this one, where this is an AND, remember there's this x multiplied by y. This is an AND operation. The Karnaugh map for this looks like this. On the top, you have the y possibilities, 0 and 1. On the vertical, you have the x possibilities, and then you just say x. Now, then in this box here, you compute the possible values of the resulting operation, and then there's some rules that apply to that. Okay, for this function, you do the same thing. You do those min terms, and then you do for x equal to 0 and 1, and for y equal to 0 and 1, what are the possibilities of these combinations, and you put it in here, and then you apply some rules. What are those rules? These are some of the rules that you use to apply. The best way of selecting 2 groups of ones form our simple Karnaugh map as shown. Okay, so you select this group of ones and that becomes your Karnaugh map. But I encourage you folks to read the Karnaugh maps. The rules of simplification are provided on the next page. Okay, so take a look at that. And there's going to be some examples on that page, but they should be relatively trivial. So that's page 151. Read that and understand it. And if you have some questions there, let me know. Okay. So groupings can only contain ones, no zeros. Groups can be formed only at right angles. Right. Diagonal groups are not allowed. The number of ones in a group must be a power of 2, and so on and so forth. So these are the rules that you use to do the simplification of the Karnaugh maps. To get a resulting outcome. Okay. We don't have to go to this one again. You can just take the same example with 2 values and propagate that to 3 values. But again, open for questions if you all have some difficulties understanding these Karnaugh maps. All right, let's see what we have here. Again, this is really supposed to be a quick brief video for you to focus on some of the things that are important. Again, Karnaugh maps, we just talked about, are very important for you to understand. Logic gates, we talked about, are very important for you all to understand. Don't care conditions. Really, not all inputs in a digital circuit are going to be used for some output. Those inputs that do not apply, we call them don't care, we don't care. And in Karnaugh maps, this is represented as x's like this. In this particular case, we really don't care of such inputs, how they impact our output. So when you're computing your output, you ignore these ones, these outputs, these results. Okay. And by the way, in the I'm going to send you guys some helpful YouTube videos that do explain Karnaugh maps. And if you have any additional questions on Karnaugh maps, please feel free to reach out. Okay. So a lot of text is dedicated to Karnaugh maps, but again, just read through it, and if you have some issues, let me know. But really, it's just an easy graphical method to simplify Boolean expressions. Okay. Now, this is Karnaugh maps, and that was section 3.4. So far, if you all have read through so far, you would have understood Boolean operators. You can fly through those chapters real quick. Karnaugh maps, I think that's the one that will give you guys a little bit of a challenge. Make sure you understand that. But once you get into Karnaugh maps, logic gates should be relatively trivial. Again, logic gates, just think about those as the device representation of those truth tables of the Boolean expressions. So those ones also, I don't expect much challenge from their Karnaugh maps. I think is the one that I expect you all to have a little bit of challenge, but again, spend some time to really thoroughly understand it, and you should be good. Once you get all through that, you start getting to section 3.5, where it starts talking about applications of all what we've learned. You start learning about digital components, right? You know, remember we talked about the logic gates. In this particular example here, you see that this is a not operation on the Y input, ended with the Z input. All of this together ORed, right? So you can imagine a complex diagram with all these components. That's what comprises digital circuitry. Okay, so that's really a digital component. And in this particular case, you can start to see how this manifests itself in the real world. You have a chip here, and these are inputs or outputs. If you look at this one, input 12 and 13 are applied in a NAND, right? Remember, there's that bubble here at the tip. So this is AND complement. And that's what goes out into pin 11. Same thing here, same thing here. So that's how you build these digital circuits with just a bunch of these logic gates. Okay. This is another very, very simple digital component. Here you have complement of X ANDed with Y. And it looks like this same circuit can be rendered like this. You know, X complement, this whole thing is a complement of X. And it's ANDed with Y, but remember, this is a complement, right? Which again, if you use one of those distributive laws, one of those laws, I can't remember which law exactly, but this is equivalent to this. Okay, and then you apply it again to one of those NOT operations. You know, the input with itself, which this is what this is, right? It gives you that. So remember, those laws, those Boolean identities, if you actually use each of those identity laws, you would be able to map out this particular example. I'll leave that as a weekly exercise for you. Same thing here. We'd have to go through that. And so these are digital components, right? Really just a collection of many logic gates. Many logic gates. Okay, so this one's just, this slide decks just give you some very practical examples of digital operations and how they apply in real world. Okay. Okay, so we sped through again this section 3.5, digital components. Again, really a digital component is all those logic gates put together to create a circuit. That's what it is. No magic there, really straightforward stuff. The key is just to be very meticulous with the inputs and the output from each gate and how it impacts the other one, and pay very close attention to those digital identities, those laws. Okay? So I think that if you all get this far, this is some good learnings. I would encourage that you read section 3.6, further reading, just to get further understanding of how digital logic gates are applied in the real world. We start talking about combinatory circuits, how you combine gates in different combinations to come up with different outcomes. You know, read through this. I don't think this should be much heavy lift. You know, how you can do carries and all those kinds of interesting things. This is addition. I recommend you folks read through section 3.6. Perhaps go through, let's see, 3.6. I'd like you all to read through just the basic concepts and the adder. You know, try to read through the adder if that is giving you too much of a head spin. Let's see, perhaps you can read the initial sections of 3.7 just to understand some of those combinatory circuits, clocks, flip-flops. And you know, if you have a lot of bandwidth, you can read through section 3.8 as well. But I would just recommend that you do a slight reading on 3.6, read the initial sections of 3.7, scan through 3.7 just to understand clocks, flip-flops. But again, given that this is a very short course, I don't expect you all to have a full grasp of these ones. But I think it's fair to ask for an understanding of how logic gates do come into play when you talk about digital circuitry, and how we can build key things from digital circuitry such as adders, clocks, flip-flops, and so on and so forth. Okay? Again, I sped through this. Intend to just give you some focus on what you should focus on this chapter. Don't, pay close attention to the Boolean operators, the Boolean identities, Karnaugh maps, the logic gates, digital circuits, and how some of those logic gates can be used to apply to build combinatory circuits, sequential circuits, and so on and so forth. Okay? I hope this was helpful. And until then, I will talk to you folks next week. Thank you.